Okay, so we said that because of the geometry of the magnetic field, Ampere's law, which is integral around the closed loop, B dot dl equals a number times some current that's enclosed. That might be useful in finding the magnetic field. Right, so similar to the ideas we use for finding the electric field via Gauss's law. Right, we needed to find a surface on which the electric field was everywhere the same. In this case, we need to find a line a path on which the magnetic field is everywhere the same. So let's say we have an infinitely long current carrying wire carrying current I star into the page. Okay, so the infinite long current carrying wire is in and out of the page, and the current is directed into the page, and we choose a circle over here. Let's say here's a circle of radius, I don't know, big R. Is this useful in finding the magnetic field? Well, what's the magnetic field? So let's say that this is red current. Doesn't really show up, but that's an excuse to make a red field. So the current is directed into the page, so dl or dr for the current. We want the field over here by our loop, and so the right-hand rule applied to the part of the Biot-Savart law tells us that here the magnetic field is pointing this way. Okay, so that's the magnetic field produced by the infinitely long current carrying wire at the location of our loop, and over here it's pointing in the same direction, but it's smaller because we're further away, and over here it's pointing in the same direction, but it's in between in terms of size, because we are a little bit further away from this, but closer compared to this. And over here the field is pointing like this, and in between the field here would be pointing and be a little bit larger than that, pointing like that. So we get a sense that it would be a complicated calculation to evaluate B dot dl or B dot dr. So let's make the dl's on the path. So this would be dl here, the dl would be that way, right? dl's are tangent to the path. That's not a great dl, but here's dl here, and here's dl here. Okay, so in some places, clearly we get a positive value. Some places it looks like we're getting close to 0. This looks like a negative value. This looks like 0. So it would be a complicated calculation, but Ampere's law makes it easy for us because all we have to do is look inside of this region, right? So that the path, the closed loop, is a boundary to a region through which we see if there's any current, and the answer is there's no current. There's no current enclosed, so that gives us 0 in this case. But it's also true that the magnetic field on the path is not a constant, right? We can see here that its magnitude is certainly changing at different places on the path. And we also have a complicated dot product. That's varying as well. It can be 0, positive, and negative at different places. So there's no symmetry here. That's not a path that's useful to us in getting the magnetic field. So we would pick, given the symmetry of the problem, given the way the current is distributed, which is into the page, we would want to choose paths that every point on the path is at the same distance from the wire, right? So something like this could be the radius big R in this case, and now we have a situation of symmetry where Ampere's law would give us the magnitude of the magnetic field, right? Because the magnetic field is circling around, and over here it's pointing this way, here it's pointing that way. This is B. Over here it's pointing that way, and here it's pointing that way. It's circling around, right? The magnetic field curls around the source, and the DLs are, in a sense, always capturing the magnetic field, because B dot DL gives us the maximum value, right? It gives us the magnitude of the magnetic field times the magnitude of DL, which is infinitesimal. They're always aligned. Sorry, I made my DLs slightly different each time. Let's make them just be consistent. Okay, so the left-hand side of Ampere's law looks like what? It looks like the magnitude of the field times the distance, because the magnetic field is everywhere the same. So basically, we're just pulling that out and integrating in dl, and that has to be equal to mu naught times the current enclosed, which is I star. So the left-hand side becomes B times 2 pi capital R equals mu naught I star. And so we can, of course, find the magnitude of the magnetic field, which we already knew was this, but we're showing how it emerges from Ampere's law. And of course, we turn that into a vector by adding a unit vector indicating that it circles around. But the magnitude of the field looks like that. And we can get it from Ampere's law in a situation of symmetry. We had to choose a path on which the magnetic field is everywhere the same. So let's say we have the current. Sorry, not a good drawing, but the current is going into the page. So here's the current, and we, instead of having a circle, we consider another closed path. There, that's a rectangle of some sort, right? What does Ampere's law say about that? Right. So this is Ampere's law. It's certainly not true that the magnetic field is everywhere the same on the sides of that rectangle. So there's nothing about the left-hand side that we can help break up this integral into something that allows us to. We can't pull the magnetic field out, certainly, but it's still true that, as complicated as the calculation seems to be around that path, B dot dl, that integral is by Ampere's law. All we have to do is, we don't have to worry about the magnetic field itself on the path. All we have to do is look at the current that's going through the region that has the rectangle as boundary. And the answer there is, of course, I star. So that's still true. When we integrate around this path, right here are the DLs, we'll get the same thing that we got when we integrated around the circle here, right? Because the right-hand side of Ampere's law is exactly the same. And when we did the integral around the circle, we got 0 here. And it's, of course, also true that if we integrate, if this is the current and our rectangle or square or whatever the closed path is out there, then what we can say is, although there's no symmetry there, it doesn't stop us from considering this integral, right? On that path, this would be 0 because there's no current through this region. So these are the DLs, and we could draw the magnetic field there. It would be something like this, where it'd be a pretty complicated calculation to do, but Ampere's law makes it easy for us. All we have to do is look at the right-hand side.